Hello, welcome to class. This is Chapter 5, Lecture 2, Part 1. I call this slide City Lights. You can see North and South America from outer space. The next slide has an interesting thought to think about, to consider, and here it is. Because humankind was created in the image of God, the human mind is a secondary and derivative source of light that reflects a creaturely way the rationality of the Creator. A harmony or correlation exists, therefore, between the mind of God, the human mind, and the rational structure of the universe. Just to think that, it's amazing to think that there is a correlation between the mind of God, the human mind, and the structure of the universe. Okay, as we continue our discussion of aromaticity, let's take a look at this. This is another example of the influence of aromaticity on chemical reactivity. In general, alkyl halides tend to be nonpolar covalent compounds, so they are soluble in nonpolar solvents and insoluble in water, as we would expect. However, cycloheptatrienyl bromide is an alkyl halide that behaves like an ionic compound, which means it's going to be insoluble in nonpolar solvents but soluble in water. It is ionic because its cation is aromatic. The alkyl halide is not aromatic in the covalent form because it has an sp3 hybridized carbon right there. The ionic form, the cycloheptatrienyl cation, trophyllium cation, is aromatic because it is a planar cyclic ion. All the ring atoms are sp2 hybridized, and it has 3 pairs of delocalized pi electrons. Being more stable, the alkyl halide will exist in the ionic form. Of course, here it is on the right. Every one of the carbons in the ring is sp2 hybridized. It's going to be soluble in polar solvents like water. This one on the left is not aromatic, and it's going to be soluble in nonpolar solvents. The resonance contributors and resonance hybrids show stability in the ionic form. So the resonance contributors of the ionic form is shown down here, and then the resonance hybrid. Let's look at anti-aromaticity. Now remember, the definition is very specific. A compound is anti-aromatic if it is a planar cyclic compound with an uninterrupted ring of pi cloud, but it contains even number of pairs of pi electrons. Instead of an odd number, it has an even number. Keep in mind that aromaticity is characterized by stability, whereas anti-aromaticity is characterized by instability. An anti-aromatic compound is a planar cyclic compound with an uninterrupted ring of p orbital bearing atoms, and the p, or the pi cloud, must contain an even number of pairs of pi electrons by Huckel's rule. Huckel would say it must contain 4n pi electrons, an even number of pairs of pi electrons. Cyclobutadiene is a planar cyclic molecule with 2 pairs of pi electrons. It is anti-aromatic, highly unstable. Now in your mind's eye, think of cyclobutadiene. 4-carbon cyclic structure that looks like a square, has 2 double bonds, one on each, between 2 carbons on each side. It's very unstable, has a small number of carbons making the cyclic structure 4, and it has an even number of pairs of pi electrons. So it is a good example of anti-aromaticity. Benzene is a nucleophile that reacts with an electrophile, forming a monosubstituted benzene compound. Why is benzene nucleophilic? Of course, it's due to the pi electrons above and below the plane of its ring. Therefore, it will react with an electrophile, Y+. When it reacts with an electrophile, a carbocation intermediate is formed. In the second step of an electrophilic addition reaction, the carbocation reacts with a nucleophile, Z minus, there it is right there, to form an addition product. Here it is. This is the product of electrophilic addition. Because the aromatic product is more stable, the reaction proceeds this way. Since this is aromatic, this one up here is non-aromatic, the reaction is actually going to proceed according to A, an electrophilic substitution reaction, rather than B, an electrophilic addition reaction, certainly because the aromatic compound is so much more stable. Here is a reaction coordinate diagram. This diagram shows that the reaction of benzene to form a substituted benzene has a delta G close to 0. The reaction of benzene to form the much less stable non-aromatic addition product is at a much higher energy. As you can see here, not as stable, and it's non-aromatic. Whereas the more stable product, as shown here as a substitution product, is more stable, it is aromatic, and it is favored. So benzene undergoes electrophilic substitution reactions. Because electrophilic substitution of benzene involves the reaction of an electrophile with an aromatic compound, it is called an electrophilic aromatic substitution reaction. In this reaction, an electrophile substitutes for a hydrogen of an aromatic compound. Of course, this is what actually happens. As we have already seen in an earlier slide, the first step is benzene reacting with an electrophile, forming a carbocation intermediate, relatively slow reaction. In the second step, a base pulls off a proton from the carbocation intermediate, and the electrons that held the proton move into the ring to reestablish its aromaticity, as you can see here. So this is fast and strongly exergonic. The proton is always removed from the carbon that has formed the new bond with the electrophile, right here. So we have a nucleophile and electrophile in the first step being very slow, and then we have a carbocation intermediate, and then the second step is very fast. Here are the 5 most common electrophilic aromatic substitution reactions. Halogenation, bromine, chlorine, iodide substitute for a hydrogen. Nitration, nitro group substitutes for a hydrogen. Sulfonation, sulfonic group substitutes for a hydrogen. Fidel-Crafts acylation, an acyl group substitutes for a hydrogen. Fidel-Crafts alkylation, an alkyl group substitutes for a hydrogen on the benzene ring. Notice in each of these cases, hydrogen is substituted in each case. All of these reactions take place by the same 2-step mechanism we saw earlier, shown in the previous slide. As we look at each of these reactions, we will notice that they differ only in how the electrophile is generated. Once the electrophile is formed, all 5 reactions follow the same 2-step mechanism for electrophilic aromatic substitution. Okay, let's look at these examples. Here's halogenation of benzene. The bromination or chlorination of benzene requires a Lewis acid, such as ferric bromide or ferric chloride. A Lewis acid accepts a share in a pair of electrons. The mechanism of this reaction is shown on the next slide. In the first step of the bromination reaction, bromine donates a lone pair of electrons to the Lewis acid, as you can see there. This weakens the bromine-bromine bond, thereby providing an electrophile necessary for electrophilic aromatic substitution. As you can see, here's the nucleophile, here is the electrophile, and we form a carbocation intermediate. And any base in the reaction mixture can remove the proton, and we form the product. as you can see here. Here's the mechanism of iodination. Electrophilic iodine, as you can see right here, electrophilic, is obtained by treating molecular iodine with an oxidizing agent, such as nitric acid. Once the electrophile is formed, iodination of benzene occurs by the same mechanisms as bromination and chlorination. And there you can see nucleophilic, electrophilic. There's a carbocation intermediate, and the base removes the proton, and we form our product. Now nitration is next. Nitration of benzene with nitric acid requires sulfuric acid as a catalyst. To generate the necessary electrophile, sulfuric acid protonates nitric acid. Loss of water from protonated nitric acid forms the nitronium ion. There it is. The electrophile required for nitration. There's nitronium ion in the next step. Notice any base present in the reaction mixture can remove the proton in the second step of the aromatic substitution reaction, forming the product. And now sulfonation. Fuming sulfuric acid, SO3, in sulfuric acid or concentrated sulfuric acid is used to sulfonate aromatic rings. Either of these cases, this one or this one. As shown above, a substantial amount of electrophilic sulfur trioxide, the sulfonium ion, is generated. So here's the generation of the sulfonium ion shown up here, and this is the sulfonation of benzene shown here. And we can have the formation of sulfonium ion either through this sequence or through this sequence. We get sulfonic acid, sulfonium ion, right here, electrophilic sulfur trioxide, and it forms and functions as an electrophile. Of course, benzene is nucleophilic. We get a carbocation aromatic intermediate. We form the product. Of course, this is a product of electrophilic substitution. It is an aromatic compound, which is more stable than a product of electrophilic addition, which is a non-aromatic product, a non-aromatic addition product. Okay, I believe we will stop right here with part 1.